Converting a Moore state machine to a Mealy state machine, that's the easy part. Making it worthwhile, that's the trick. A Mealy state machine, where the output is dependent on both the current state and the current input, is a little bit more difficult to design than a Moore state machine, where the output is only dependent on the current state. But it could be worthwhile because the Mealy state machine typically has fewer states than the Moore state machine does. In order to outline the conversion process, let's go back to our old friend, the regular expression where we were looking at coin tosses. Any sequence of coin tosses where the last two coin tosses ended up in a tails, excuse me. So we have heads or tails, any sequence, and then the last two have to be tails. Now, the state diagram, the Moore state machine for this, had 3 states. So we had 1, 2, 3 states. All right, and I'm going to put this little line where we can have the state name up top. So Q1, Q2, and on the bottom half, we were going to have the output. Now Q0, that was our initial state. Now anytime we got a heads from any state, we kind of reset, right? We came back to Q0 where we were waiting for any sequence of tails. We got the first tails brings us to Q1, and then the second tails brings us to Q2. And anytime we got a tails in Q2, we stayed in Q2. So 2 tails, ending in 2 tails, we get to Q2. So Q2 is our accepting state. Now in our introduction to output, we actually talked about a light bulb being off until we got to the accepting state. It would be on in the accepting state. But what we're just going to do is simply say, no, we don't have it. No, we don't have it. Yes, we have it. All right, so there's our output. Now, in order to do the conversion process from a Moore machine to a Mealy machine, we're going to use the transition table. And so the transition table, I had my current state. And in the case of this Moore machine, I had 3 of them. I had Q0, Q1, and Q2. My initial state is Q0. Now, the standard transition table, I have my list of inputs, all the possible inputs. So I've got my heads and I've got my tails. And I need to show what I'm transitioning to from each one of these states for this deterministic, fully deterministic state machine here. What I've got is a heads from any of my states brings me back to Q0. All right. Remember, I always go to Q0 whenever I get a heads because I'm starting over to look for those 2 tails. Now, if I get a tails from Q0, I go to Q1. If I'm in Q1 and I get a tails, I go to Q2. And once I get to Q2, tails are going to keep me in Q2. Now, let's look at the output. For our Moore machine, remember, we're going to map our output, our current state to our output. So Q0, no. Q1, no. Q2, yes. That's our Moore machine. Now, to actually convert this from a Moore machine to a Mealy machine, turns out it's pretty easy. All we have to do is simply say, okay, what state am I going to? Well, the state I'm going to, what's its output? I'm simply going to associate that output with that transition. So if I'm in Q0, if I'm going to Q0, Q0's output is no, right? Q1's output is also no. So notice all I'm doing is I'm simply saying, here is my destination state. I'm going to convert this to a Mealy machine, I'm simply going to say that the output corresponds to the state that I'm going to. Now I've got my output associated with the transition instead of being associated with just the state. So if I'm in Q1, when I go to Q0, Q0 has an output of no, so that transition is now going to have an output of no. Q2 is going to have an output of yes. Notice we have the relation, Q2, output of yes, so that transition now gets an output of yes. Now, Q0 from Q2 is no, Q2 is yes. So once again, all I'm doing is I'm saying instead of associating the output with the state, I'm now associating the output with the transition using the same correlation for the current state. So now all I need to do is just erase this output column, and poof, I've got a Mealy machine. But this Mealy machine has exactly the same number of states as my Moore machine, so really there is no benefit to make the conversion. How are we going to take a look at converting this into a Mealy machine? Well, the Mealy machine, what you do first, so this is actually a multi-step process. Step one says, what I'm going to do is I'm going to group these states together based on a common output for each one of the inputs. Let me try that again, because what we're looking at doing is grouping together states that have a common destination and the same output associated with that destination. So if you look at this table here, the first state has an output of no for all of the inputs. So any other set of transitions that also have no and no, a no for heads and a no for tails, they're going to be in the same group. Well, it turns out there are none. So this guy right here is a group unto itself, all right? Now, both of these last two states, Q1 and Q2, for heads, they both output a no. For tails, they both output a yes. So we're going to group these two together into a common set, Q1 and Q2. Now that we have grouped our states into the states that have the same output for each one of the inputs, now we need to see if they need to be broken down any further based on the destination. In other words, I want to make sure that for heads and for tails, that both of these transition to the same sets of states. If they transition to the same sets of states, then I know that I've got a good grouping here. If they transition to different sets of states here, I have to break them down. I need to decompose them into a little bit further down and keep doing that until there's no more decomposition. Let me try and do this with an example. And the second example, hopefully, will make this a little clearer. Now, once you have a group or a set that just has a single state, can't decompose that any further. So that one we don't have to look at. But this one, since I have two states in this set, I need to make sure that this state transitions to the same set of states as this one. So let me try that again. So if we've got heads, we don't need to look at the output anymore. If we've got heads, both Q1 and Q2, they both go to Q0, which is the same set of states. For Q1 and Q2 tails, they both go to Q2, which is the same set of states. So it turns out that both Q1 and Q2, not only do they have the same output, but they also go to the same set of states based on the input. So I'm going to simply relabel this. I'm going to call this one A. I'm going to call this one B. So now I have fully simplified this Mealy machine into two states. So this set and this set, they actually are the only two states we need for this Mealy machine. Now all I need to do is rewrite my transition table in order to match these two states rather than the original three. What I'm going to do is anywhere I see a Q0, I'm going to replace with A. Anywhere I see a Q1 or a Q2, I'm going to replace with B. But notice that Q1 and Q2 are in the same set, so I don't even need to have Q2 any longer. And so now it's just a matter of replacing Q0 with A and replacing Q1 and Q2 with B. What does it look like whenever we're talking about the state diagram? Well, let's draw it. I've got two states. I've got A and B. From A, if I get a heads, I come back to A with no being the output. If I have a tails from A, I go to B. So that's a tails with no as the output. If I'm in state B and I get a heads, I go to A with the no output. And if I'm in state B, I go to state B with the yes output. And there's my fully simplified Mealy state machine for that sequence, for that regular expression. What we're going to do is make a state machine that is going to take as its input the binary alphabet, and it's looking for the sequence 0101. This happens a lot whenever we're talking about digital communications. You're looking for a pattern of ones and zeros to trigger something, either the start of a message, or in fact, sometimes we have, like, if we get more than 4 ones in a row, in order to keep synchronization, we do something called zero insertion in order to verify or that we're going to at least get some bit changes. There's a number of reasons why we would look for a pattern. This pattern is pretty simple. In fact, we're going to have just 5 states in our more machine. We're going to have the first state, which is I don't have anything yet. The second state, which is I've got the first bit. The third state, which is I've got the second bit. The fourth state, which is I've got the third bit. The fifth state, which is I've got all the bits. I've found the pattern. So I've got 5 states here. 1, 2, 3, 4, 5. And they're actually going to kind of go like this for our more machine. So if I get from the first state, we'll call this Q0, we'll do Q1, Q2, Q3, Q4. What we're going to do is we're going to say if I get a 0, I go to the second state. If I get a 1, I go to the next state. If I go a 0, I get the third state, and I go to the last state, or excuse me, the fourth state. And if I get a 1, I go to the last state. So what we've got is no, 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 yes. Now, we're missing some transitions. This is not a fully deterministic, finite automata. So what happens is if I'm in Q0 and I get a 1, I'm going to still be waiting for the first bit. I haven't got the first bit of the sequence. Now, if I'm in Q1 and I get a 1, that means I've got the second bit. But if I get another 0, that means that the first 0 that brought me to Q1, that wasn't the first bit. But maybe this second 0 is the first bit of that sequence. Okay? So as long as I keep getting 1s, I've got nothing. And whenever I get my first 0, that could be the first bit. If I get another 0, that means that first 0 wasn't the first bit, but this one might be. If I get a 1, then that means I've got a 0 and a 1, and I might have the first 2 bits. If I'm in Q2, then I get a 0, that means I could have the third bit. If I get a 1, what that means is I got a 0, followed by a 1, followed by another 1, which doesn't look like anything in this pattern. So we go back to the first state, the starting state, which says, okay, we got to start over from scratch. So I've got my 0 and my 1, my 0 and my 1, my 0 and my 1 out of the first 3 states. Let's take a look at the fourth state. So the fourth state, if I get a 0, what that means is that I got a 0, 1, 0, 0. That means that I did not have this pattern, but this latest 0 could be the first bit of a new pattern. So it brings me back up to Q1, which is may have the first bit. Now, if I'm in Q4 and I get a 0, Q4 means I got 0, 1, 0, 1. So I got 0, 1, 0, 1. If I get a 0, that means, well, this was the pattern, but this 0, 1, 0 may also be the pattern. So 0, 1, 0, that may be the first 3 bits, which brings us to Q3, which is I might have the first 3 bits of the pattern. If I am in Q4 and I get a 1, that would be 0, 1, 0, 1, 1. That does not look like any portion of the pattern, and so I go back to my initial state. So there you go. That is the state diagram, the state diagram for this pattern detection. All right. Now let's do what the transition table looks like. For the Moore machine, the transition table is going to look like this. First of all, we have the 1, 2, 3, 4, 5 different states. Q0 is our initial state. And we have our input alphabet 0 and 1. And what we had was, if we get, so our 0 from Q0 is going to take us to Q1. And then when we're in Q1, if we get a 1, we're going to Q2. And then if we get a 0 from Q2, we're going to Q3. And then if we get a 1 in Q3, we're going to Q4, all right? So that was what took us through the pattern, right? Now, what happened in Q0 if we got a 1? Well, remember, in Q0, if we got a 1, we stayed in Q0 because that meant we didn't get any of the pattern. If we were in Q1 and we got a 0, that meant the first 0, the one that brought us to Q1, was wrong, but maybe this one is right, so we stay in Q1. If we're in Q2 and we get a 1, well, Q2 and get a 1, that meant that we got a 0, 1, 1, which isn't anything of the pattern, so that brings us to Q0. If we're in Q3 and we get a 0, that means that we got a 0, 1, 0, 0, which means that those bits were wrong. They didn't give us the pattern, but maybe this last 0 is the first bit of the next pattern. So we go to Q1. Now, if we're in Q4, that means that we got a 0, 1, 0, 1. If we get a 0, that means that we could have the 0, 1, 0 of another pattern. So remember, that is going to bring us to Q3. All right. But if we got a 1, that means we got a 0, 1, 0, 1, 1, which means we have nothing, which brings us back to the initial state. Now, let's take a look at our output. So basically what we're saying is that none of these states, right, we're associating the state with the output, none of those are going to give us a, yes, we got it. The state Q4, that's the only one that says, yes, we've got the full pattern. So how do we convert this to a Mealy machine? Well, remember, the conversion to a Mealy machine was really easy. All we did was we took a look at each one of these states and simply said, well, what was the output for these states? There we're going to associate that output with that transition. The conversion was easy. It was the simplification that was a little bit more difficult. But let's go ahead and do this. Q1 has an output of no. Q1 has an output of no. Q1 has an output of no. All right, that's all our Q1s. Now, Q0 also had an output of no. Q0, no, no. Q2 had an output of no. So we make that transition right there. Q3 also had an output of no. And Q4, that was the only one that had an output of yes. All right, so there is our transition table for the Mealy machine, the not simplified Mealy machine. Now let's see if we can't simplify it. Remember, step 1 said, what we're going to do is we're going to look at or group together the states that had the exact same output. So let's, for each one of the inputs. So notice that Q0 has no, no. Q1 has no, no. Q2 has no, no. Q3 has no yes. Q4 has no, no. So we're actually going to create our first set that is going to contain Q0, Q1, Q2, and Q4. All right, because those all have the same output, no, for both the transitions. We are going to take Q3 and we're going to make a set by itself. So we've got this set A and this set B. Now, that is just simply mapping and making sure that the outputs match. Now we have to make sure that the destination matches. In other words, I've got set A and set B. I need to make sure that for 0 and 1, for everything in this set, they all go to either go to this set or this set, they match, all right? This guy, Q3, it's already fully decomposed all the way down to the bottom. We can't break that down anymore, so we don't need to worry about Q3 anymore. So we're going to start out, I'm going to call this just A and this one B. And I'm going to see what happens for 0 and 1, and 0 and 1, and 0 and 1, and 0 and 1 for each one of those. And the ones that go to the same set, that's going to be our new state set. So for Q0, if it's a 0, I go to Q1, which is in set A. And if it's a 1, I go to Q0, which is also in set A. So both 0 and 1, it stays in set A. Q1, if I get a 0, I go to Q1, which is in A. If I get a 1, I go to Q2, which is also in set A. For Q2, if I get a 0, it goes to Q3, which is in set B. So I automatically know that Q2 is not going to be in the same group or the same set as Q1 and Q0. Q2, whenever it's a 1, I go to Q0, which is in set A. Q4, whenever I'm a 0, I go to Q3, all right, which is set B. And when I'm a 1, I go to Q0, which is in set A. So look, Q0 and Q1, they go to the same places for a 0 and 1. For Q2 and Q4, they go to the same places. So I've got two new sets. I've got a Q0, Q1 set, a Q2, and a Q4 set. B, the Q3 set, that's already standing by itself. Let's go ahead and see if those decompose anymore. All right, so we first broke into different sets based on the output. Then we made sure that our target or our transition, our destination, our next state, that broke us down into these three groups. I'm going to call these A, B, and C. Remember, Q3 is already broken down as far as it can go, but let's make sure that these guys can stay together. All right, so what happens if we get a 0 and a 1 from Q0? A 0 and a 1 from Q1, a 0 and a 1 from Q2, a 0 and a 1 from Q4. All right, so if we're in Q0, a 0, Q0 brings us to Q1, which is in set A. A 1 from Q0 brings us to 0, which is in set A. Q1, a 0 brings us to Q1, which is in A. A 1 brings us to Q2, which is in set B. So these two are going to have to be broken down again into two separate groups. However, B, let's take a look at B. If we're in Q2 and we get a 0, we're going to Q3, which is in set C. If we get a 1, we go to Q0, which is in set A. Q4, if we get a 0, we're going to set C. If we get a 1, we're going to Q0, which is in set A. So these two can still be together, but this is going to have to break, we're going to have to break A into two pieces, one set for Q0 and one set for Q1. Let's do that one next. All right, now we've got four sets. Breaking it down, we need to see basically there's only one set that has more than one state left in it, and that's set C. We need to make sure that their destination sets are the same for both Q2 and Q4. These are already broken down as far as they will go. So Q2, we need to figure out what happens for a 0 and a 1. We need to figure out what happens for a 0 and a 1 for Q4. For a 0, Q2 goes to Q3, which is set D. For a 1, Q2 goes to Q0, which is set A. All right. Q4, whenever you get a 0, we're going to Q3, which is set D. And when you get a 1, we're going to Q0, which is set A. And we actually could have seen that because if you look at these guys right here, you see that Q3, Q0, they're the same. No, no for both of those. You could have seen that, but what I wanted to show you was that you keep doing this until you get it to stop breaking down anymore. So what we've got is our fully simplified Mealy machine is going to have these four states, A, B, and C. So let's go ahead now and create our simplified state transition table. We're going to do that by saying, okay, A, B, D, those are already one state. So those are actually going to be replaced in our transition table exactly the way they are. But Q2 and Q4, we are going to merge into one state. And what I'm going to do is I'm simply going to take everything that's Q4 and I'm simply going to make it so it's Q2. So we're going to get rid of our Q4 line right here. All right. Now, everywhere you see a Q0, we are going to substitute A. So Q0, we're going to substitute A. All right. So we've got A. All right. And let's see, Q1. Everywhere we see Q1, we're going to substitute a B. So those two. Anything else? There's one down there. All right, I don't see any others, so we've got B, 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 B. All right, now Q2 or Q4, we're going to substitute C. So we got Q2 and Q4. All right, we're going to substitute C for that. And then Q3, that's where we're going to put D. All right, and there's our Mealy machine. Let's draw the state diagram real quick and just get an idea of whether or not it will work. All right, let's create our state diagram from our state transition table. So I've got 4 states. I've got A, B, C, and D. And what we've got is an A is our initial state. All right. If I get a 0, I'm going to B with a no. So 0, no. If I get a 1, I'm going to A with a no. So 1 brings me to A with a no. If I'm in B and I get a 0, I'm going to go back to B with a no. All right, and this doesn't look that different than our first state machine, where as long as I keep getting 1s, I haven't found any of the pattern. When I get my first 0, I'm going to could have the first bit state, and as long as I keep getting 0s, I'm going to stay there. Now, if I'm in B and I get a 1, then I am going to C with a no. If I'm in C and I get a 0, then I'm going to D with a no. If I get a 1, I'm going up to A with a no. If I'm in D and I get a 0, I go to B, so that's a 0 with a no. If I'm in D and I get a 1, I'm going to C with a yes. All right. Now, does this work? Is this correct? Well, let's do a couple of sequences. As long as I keep getting 1s, I'm staying in A. But if I get a 0, 1, 0, 1, I output a yes. And in fact, as long as I keep getting 0, 1, 0, 1, 0, 1, I'm going to keep outputting yeses for continuing to get that pattern repeating or embedded in itself. All right. If I keep getting 0s, I'm going to stay in state B until I get a 1. If I get a 0, 1, 1, 0, 1, 1, which is not that pattern at all, it brings me back to the reset state. Looks good. You take a look at this and tell me if that fits our original definition of the problem. Now, if you're interested in how all of this gets implemented in real hardware using logic gates, go check out the videos in our computer organization series.